Right, let's go with the title of equilibrium of rigid bodies in three-dimensional space. Now, the logic is, again, the procedure is the same. The approach for modeling and analyzing or studying the rigid body objects in three-dimensional space is the same. In this case, we cannot simplify this. Obviously, everything is happening in three-dimensional space in real life. When we look at rigid bodies in two-dimensional space, we're simplifying what is happening in reality because all the forces are in a plane. Right? Now, when we if we have a force or forces that are not, or all of the forces are not in the same plane, then we're talking about uh, analysis in three-dimensional space. Now, the difference is, well, the procedure is very similar, as I said. We draw a free body diagram in three-dimensional space, then write the equilibrium equations, and just solve for the unknowns. The difference is, well, as I said before, let me just before move forward, let me put a few words here. The approach uh, for modeling and analyzing, say, rigid bodies in three-dimensional space or 3D is the same as 2D. That's pretty much it. So what we do is that we draw the free body diagram, draw a free body diagram, depending on which part of the rigid body or which specific rigid body we are interested in within a system. And then let's say solve the equilibrium equation, I guess. Equilibrium, or let's put it this way, then write down the equilibrium equations. Now, what changes is that now we have more equations, and as a result, we can deal with more unknowns. Right? We can deal with up to 6 unknowns because we are going to have 6 equations. So just quick note now. Uh, well, in 3D, you can say we have more variables. Right? As a result, we can have more unknowns. So you draw the free body diagram, look at all the possible forces. When you isolate this as a specific part of the system, when you look at all the forces, we just write down the equations again, right? For that specific part. Summation of forces should be 0. Remember, this is a vector. I write it as different components, but the way we deal with it is the way we deal with vectors in 3D. But generally speaking, you get an equation in each direction. You get an equation in x direction, you get an equation in y direction, and an equation in z direction. At the same time, we know summation of moments should also be 0 about some point, let's say O. And let me just not put the direction here. Let's just represent this. Obviously, it's a vector. Summation of moments should be 0. As a result, summation of moment in x direction is 0. Summation of moment in y direction is 0. Summation of moment in z direction is 0. And that's what I mean by we are going to have 6 equations. If you separate everything, right, just force in x, forces in y, and forces in z, moments in x, moments in y, and moments in z, right, you're going to have 6 equations. So as a result, in three-dimensional space, we can afford having 6 unknowns maximum. Now, if you remember when we were talking about forces, right? We said there are four forces. You should know that by now. Can someone mention those forces we had for when we were looking at the equilibrium of particles, not just rigid bodies, just particles. We have weight, exactly, right? We had cables and tensions, exactly. Cables, ropes, chains, which are always in tension. We have normal forces, which is called it smooth contact. And we have a spring. Exactly. Thank you. So these four forces. Whenever you isolate something from the system, you want to draw a rigid body, remember these four forces up to here in this course until we get into friction. Remember these for, actually for rigid bodies, we take into account friction by saying if there is a friction on the surface. So when you have a support, we can take into account. So scratch that. So these four forces, plus we said when we deal with rigid bodies, we have another set of forces that are support reactions. We call them support reactions. We said whenever we have these supports in the system, what do? Is that when we isolate the system or the part of the rigid body that we are, a part of the system, in this case a rigid body, we have to replace those supports with appropriate forces and moments associated with those supports. Now, here is the difference between two-dimensional and three-dimensional space. Right? Aside from the fact that we can deal with 6 unknowns, we are going to have more unknowns because the support forces or reactions in 3D are going to be different. So I won't talk about force, spring force, weight, smooth contact, or cables and ropes and chains or tension forces in these. Obviously, they're always in tension because they are the same as what we had for a particle in three-dimensional space. The only thing is that you have to remember they are vectors in space, so you have to write them in Cartesian coordinates. The only thing we have to add now to our explanation, and we have to study, and the only things that are new now in three-dimensional space is that we're going to look into different supports. Right? We looked into different supports for two-dimensional space. If you remember, we had 5 supports, and each type of support was giving us different number of unknowns. The maximum number of unknowns was for cantilevers or fixed support. For a fixed support and fixed support, if you were removing that specific support, fixed support, we were getting, we had to replace that support with 3 forces, or 1 force with an unknown direction and a moment. We had to replace it with 2 forces and a moment, or 1 force, an unknown direction, and a moment. Other forces, depending on what we had, is simple. It's a roller. It's other type, other types of supports. We went through that table again. There are 5 types. We had to replace those types of reactions, support reactions, with appropriate forces when we were drawing free body diagram for rigid body. Now, so the next step, natural step, would be, well, we know how to isolate the system by now, draw a free body diagram. While writing these equations, as long as we have these moments and forces represented in Cartesian coordinates, it's not a very, it's a very straightforward procedure. Again, longer in 3D space, but still same same procedure. And remember that when we were talking about the equilibrium of points in 3D space, we did not have the equations for moments, right? Equations for moments here, summation of all the moments around specific point equals to 0, is added because we're looking at rigid bodies. Let me put it here. I want to make sure that these are connected so you know where we're going. So for rigid body, right? For a rigid body, sorry, let me write it this way. For a point or particle in 3D, we had these equations. For a rigid body, this was all the equations we had to, or we had access to, or we could use to find unknowns or analyze the system. They were for rigid bodies in 2D space. Now we have an added equation for force and an added equation for a moment.